So we've come up with an explanation for dwarf novae explosions. We have white dwarf, this incredible hellish dense object, and we're dumping matter from a star into it, and there's a rather complicated system whereby the matter smashes into a disk, producing a flickering hot spot, and then builds up in the disk and then dumps huge stuff in the middle. I mean, surely it can't get much more violent than this, can it?
Well, I think we must call them dwarf novae for a reason, Paul. And indeed, there's something that we call classical novae, or just novae, which are many orders of magnitude brighter. So, for example, there's a very famous one called RS Ophiuchi, and you can see it's down here, and it gets 10,000 times brighter, and then fades away.
Remember, the dwarf novae are only getting 100 times brighter, so in the scheme of violence, they're pretty pathetic compared to this.
Yeah, and the interesting thing about this is this object doesn't repeat every month. It repeats every 20 years or so, and some of them repeat after hundreds of years.
In fact, the definition of a classical nova is it doesn't repeat. Of course, they probably do repeat. It's just that we haven't been observing long enough to see them repeat. So probably there are differences between so-called recurrent novae and classical novae, but they're probably all the same thing. A recurrent nova is one where we've seen at least 2 explosions. Classical nova is one where we've only seen 1 explosion so far, but they're by and large the same thing. And there's got this huge increase in brightness.
They're quite interesting if you look at them after an explosion. So here's another one, and you can see after the explosion, you're able to look at it, and you can see that there's this big shell that gets bigger and bigger over time, and it's sort of shooting material out 2 directions, sort of like, I don't know, I guess a gun, if you manage not to have a stock when you shot it off, it goes out both directions.
Yep, so that's a bit weird. I mean, the classical novae, the explosion is caused by stuff going in. We're not seeing any blast wave come out, but here we really are seeing a blast wave coming out, which is a bit different.
Yeah, and we think this stuff is dust, so probably there's explosion stuff there, but there's a ring of material around it you can't see.
Yes, that's making it a bit puzzling, because the dwarf novae were caused by gravity, stuff falling in, and that's not really going to get our stuff going out, is it?
Well, I guess it all depends on whether or not we can make enough energy, because the energy of whatever creates one of these things is the thing that will eventually push material out. And presumably if you make a big enough amount of energy, you'll make a big enough bomb to make something that looks like what we see.
So, any clues about what's going on here? Well, there is this is an absolutely wonderful clue. Nova Persei 1901 went off in 1901, curiously enough, and you can see it's blown a whole shell of stuff out. It's now quite large and quite pretty. But there's a real clue here, because if you look in the centre now, you see a dwarf nova.
Ooh, that is an interesting clue, isn't it?
So it looks like the dwarf novae and the classical novae are actually kind of the same thing. 2 different ways in which the same thing can explode.
So that suggests that we have a white dwarf, once again, responsible for what's going on.
So it looks like we need to find another way to get an explosion out of a system like this. We've got a white dwarf again, presumably because it's acting like a dwarf nova, gas is being dumped on the surface. How can we get an explosion? The dwarf nova explosion we got from gravity, so matter would pile up in the disk, and then as the gravitational potential was released as it fell in, you get an explosion. But that's far too small to produce these classical novae, unless we dump 100 times more matter down. So is there some other energy source we could use?
Well, Paul, if we think of the star in the sky we see every day, which is the sun, we think the sun was powered by gravity only for the very few well, not minutes, but years of its lifetime. And since then, it's been powered by nuclear reactions of hydrogen into helium.
Well, that can't really work here. I mean, nuclear fusion releases huge amounts of energy when you turn hydrogen into heavier elements. But we've already said the density here is so, in the middle of a white dwarf, is so immense that if it was hydrogen there, it would have turned into a star. It wouldn't be a white dwarf. So it must be made of something that doesn't fuse as easily. So probably carbon and oxygen left over from the star that formed it. And carbon and oxygen don't fuse very easily. It takes a lot more pressure than we've got in a white dwarf to make them fuse.
It is certainly true, but around this white dwarf in this model, we have a bunch of junk from that star. It's almost certainly going to be hydrogen, so clearly there's going to be hydrogen around. It's just a matter of making it, configuring it in a way so that it can lead to some sort of nuclear reaction.
Yeah, so presumably we've got this core of carbon and oxygen, which can't fuse in the pressure we've got here, even in the hellish pressure of a white dwarf, but we're going to be getting this layer of hydrogen building up on the surface. So sort of like hydrogen snow or something raining down steadily on the disk around the centre, but then presumably flowing around the surface of the white dwarf, because the white dwarf's pretty hot, it's going to be pretty fluid. So you're going to get an ever thicker layer of hydrogen. So maybe we could get some fusion happening at the bottom of this layer where there's a pressure. But that doesn't seem to make sense to me, because, I mean, this is a very thin layer of hydrogen. If you look at the sun, you've got this huge great blanket of hydrogen, but the fusion is only happening in the central 0.5%. The other 99.5% of the star is just an immense blanket to squash down that middle 0.5%. How can a really thin layer, like on the surface here, do anything?
Well, okay, Paul, remember our white dwarf is incredibly massive and very compact. So it has a huge amount of gravity. So we go through and calculate, for example, the force on a little parcel of hydrogen. It's your normal equation of G big M, that's going to be the whole star, little m, which is our little piece of hydrogen, and then the radius squared. But this radius is tiny. Instead of, it's 100 times smaller, the white dwarf, than the sun. So that means that's going to be 100 squared, or 10,000 times smaller number, meaning the force is going to be 10,000 times bigger.
Yeah, and so in any sort of star, you're balancing pressure against gravity. So in the middle of the sun, the pressure in the middle has to balance the mass of that enormous blanket of hydrogen. And so if the hydrogen's pressing down hard, there must be more pressure in the middle. Here what we're saying is that the gravity is going to be 10,000 times stronger at the surface.
Yes.
So a layer 10,000 times thinner will still have the same pressure at the bottom, roughly speaking. So that means you really can get away with just a very thin layer on the surface, 1/10,000th of the thickness of the star, and still have the same pressures that would start nuclear fusion.
Right. So it's a great way to think about how to generate all that energy. But it's also a place where hydrogen is in a particularly interesting form that we need to talk about.